Recursion forms the base for many commonly used algorithms, which is why it often comes up in technical interviews. That's why in this video, we are going to make sure we learn all about recursion, when it's best to use it. Then we are going to solve some of the most common technical interview questions that require the use of recursion. Of course, we are going to do all of this using JavaScript. Let's get started. So what is a recursive function? A recursive function is a function that calls itself. For example, let's create a very simple function whose only purpose is to console log the word hi, and let's call it and check the console. We can see that the word hi is logged only one time. Okay, now let's see what happens if we call the function within itself. Oh wow, it just keeps printing hi, 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 and it doesn't look like it's ever going to stop. So let's break down what's going on. So first the function calls itself, then it logs hi to the console, then it calls itself again, and then it calls itself, logs hi into the console, calls itself, and so on. It's an infinite loop, which means our function will keep running until our program encounters a Stack Overflow error or an error of some kind that forces it to stop. To prevent a function from endlessly calling itself and creating an infinite loop, we need to create a stop condition, which is also referred to as a base case. A commonly used base case is specifying the number of iterations or how many times we want our function to run. Let's begin by adding iterations as a parameter to our function. Now let's go to where we recursively call the function within our function and subtract 1 from the number of iterations. That way, every time the function calls itself, the number of iterations will be reduced by 1. Okay, now let's write our base case or stop condition. So we want our function to stop running if iterations is less than or equals 0. So if iterations is less than or equals 0, return. That should stop our function. Okay, now let's go to where we call our function and specify the number of iterations we want. Let's equate it to 6 iterations this time. That should mean that our function should run 6 times. So now we know that recursion is a programming concept where a function calls itself during its execution. We also know that a recursive function typically has 2 components, the base case, which is the stop condition, and the recursive case, which is the part where the function calls itself. Now let's discuss the use cases of recursive functions. But first, I would like to ask you to subscribe if you haven't already, and if you liked the video, please hit the thumbs up button. Now let's discuss the use cases of recursion, particularly when it comes to technical interviews. Recursion forms the base for many other algorithms that tend to make an appearance in so many technical interviews, such as divide and conquer algorithms, tree traversals, and backtracking algorithms. Let's start talking about divide and conquer. Divide and conquer is a problem-solving strategy that involves breaking down a complex problem into smaller, more manageable subproblems. A great real-world example of using a divide and conquer approach to solving a problem is when we need to look for something that we've lost around the house. Instead of trying to search the entire house, we can subdivide the problem into smaller parts by looking in each room separately. Now let's examine a problem that often makes an appearance in technical interviews. Okay, let's say we have a sorted list like this one, and we are asked to find a target in it and return the index of that target. So let's say our target is 35 and our mission is to return the index of 35, which in this case is 6. So how can we do this? We could try applying a linear search and go through the numbers one by one. You could start with the number that corresponds to the index of 0. and check if it's our target. In this case, it's 3, definitely not our target. Okay, then we go through the second number. Nope's not our target. The third number, nope's, until we get to our target. As you can imagine, this is not the most efficient approach, especially if we have a large data set. Let's try a much more efficient approach, which I promise will be super duper easy and fun. It's called binary search. The first step to a binary search is finding the middle element. In this case, it is 17. And we compare this mid element to our target. Is the mid element our target? The answer is no, it is not. Okay. Is the mid element greater than or smaller than our target? 17 is smaller than our target. Okay, so since this is a sorted list and all the numbers that are before 17, all the numbers on the left are also going to be smaller than our target, then we can just eliminate them. We are not going to go through them because we know they won't match our target. They're smaller. All right, so now we have these elements left. We're going to repeat the same process. We're going to find the mid element. In this case, it is 66. And then we're going to check if it matches the target element, and it does not. It's not equal to 35. It is actually greater than 35. So we know that none of the elements to the right of our mid element will be the target because they're all bigger. So now we have two numbers left, 28 and 35. We'll consider 28. Is it our target? No, it is not our target. There's only one number left, and that number has to be our target. So we will return the index 6. I think we're ready for writing a recursive binary search function that returns the index of a target element in a sorted list. Let's start defining our function. Let's call it function binary search. And it's going to take a bunch of params, the first of which is the array that we are going to search through. The second of which is the target that we're going to search for. And then left, which represents the index of the leftmost element, which would be 0. And then right, which represents the index of the rightmost element, which would be equal to array dot length minus 1. Okay, and now let's start defining our base case. So if left, which is equal 0, is greater than right, return -1. Let's define the recursive case. And the recursive case will follow the steps that we have applied in the example. So the first thing we want to do is we want to find the mid element. So let's declare a variable mid where we're going to keep the index of the mid element. So const mid would be equal to math.floor left plus right over 2. And now let's check if the mid element matches our target. So array with the index mid, if array with the index mid equals our target, then we want to return mid. Okay, else if the mid element is smaller than our target, then we want to run our function again. And we'll pass in the array, of course, and the target. They stay as they are. Next up, we need to pass in the value for left. And here we want left to be mid plus 1. Because if the target is bigger than our mid element, then we want to consider the elements to the right of our target, and we no longer want any of the elements to the left of our targets. Therefore, left now equals mid plus 1. So the smallest element here would be the element right after our mid. That's why we're adding 1 to the index. Right would stay as it is. Else, if the target is smaller, then we would want to search in the left half. So return, we want to run our function also. We'll pass in the array, target, and we want to search in the left half, so left will stay as it is, and right would be mid minus 1, since that would equate to the index of the number right before the index of our mid. Okay, let's try our function. Let's add in the sorted array that we have played around with earlier in our example. Okay, and let's add in the same target value. So const target equals 35. And now console log binary search. And we want to pass in our sorted array and our target. All right, let's run our function. Yay, we got 6, just like when we tried it out earlier without using coding. Binary search is good with recursion because it chops the problem into smaller parts, deals with one part at a time, and then puts everything back together to solve the problem. This approach is called divide and conquer. Use divide and conquer when you can break a problem down into smaller, similar parts, solve each part independently, and then combine the solutions for the overall answer. Candidates are often tested on tree traversals and technical interviews. In computer science, a tree is a hierarchical data structure that consists of nodes connected by edges. Each node has a value, and these nodes are organized in a branching structure. The topmost node in the tree, from which all the other nodes are descended, is called the root. In plain English, traversal means travel across. So tree traversal is when we travel across a tree and visit and process each node in that tree. Some of the most commonly used tree traversal algorithms are depth first search algorithms, which include Inorder Traversal, Preorder Traversal, and Postorder Traversal. The main difference between them is the order in which each node is visited and processed during the traversal. Let's set up a binary tree to see how Preorder Traversal, Inorder Traversal, and Postorder Traversal work. To do that, let's start defining class tree node that we will use to create the tree. We would like to be able to pass in value as a param. Other than that, each tree node should have 2 attributes, which are left and right, and both of which should be set to null. Now let's use this class to create our binary tree. So let's begin with the root. Root, new tree node. Let's give it the value of 1, and node 2. Let's give it the value of 2. Const node 3. Let's give it the value of 3. And let's keep going like that and create 7 nodes. And now let's assign the attributes left or right to our nodes. To create a structure, we basically want to make our tree look like this. So root.left equals node 2. We want node 2 to be the left child of our root, node 3 to be the right child of node 2, and the left child of node 2 should be node 4, and so on. Okay, let's define the Inorder Traversal function. It should take in root as a param. And since we want to return the node values as an array, let's create an array to keep the values and call it result. Let's create a helper function where we are going to carry out the recursion. Using a helper function in the context of recursive tree traversal is a common practice to encapsulate the recursive logic and manage additional parameters or state. It can also make the code more modular and easier to understand. Our helper function will take in node as a param, and our base case is if node is null. In order to be able to write the recursive case, we should first remind ourselves of the pattern of Inorder Traversal, and it is left, node, right. So traverse node dot left and result dot push node dot value, and then traverse node dot right. Okay, and that's called the helper function. So traverse route, and finally return result. Okay, so now we need to make sure that our function works correctly. So let's console log and call in our function and pass in the root of our tree. Okay, let's run it. Okay, how do we know that this is the correct answer, you may ask? That's a good question. So I've actually decided to create this particular tree because there's an article using it on Geeks for Geeks, and they have the tree already traversed, and I thought this could be a simple way to verify if our function works correctly. And looks like our function works correctly since the values match. All right, let's code the preorder traversal function. Since it's going to be very similar to the Inorder Traversal function, what I'm going to do is I'm just going to copy the Inorder Traversal function and I'm gonna paste it, and then I'm going to change some things. So let's call it Preorder Traversal, and this remains the same. We're also gonna have a helper function over here, but the pattern for Preorder Traversal is different, and that's what will change. We're going to change the recursive case. For Preorder Traversal, the pattern is node, left, right. So it should be result dot push node dot value and traverse node dot left, and finally traverse node dot right. Okay, and now let's test our function. It matches the pattern here as well, so we did it. Let's define postorder traversal function. Let's copy our preorder traversal function and paste it, change the name of the function. And what we're gonna change is the recursive case. Postorder traversal follows the pattern left, right node. So let's delete this. So first we want to traverse the left node, so node dot left. Then we want to traverse the right node, so node dot right. And then we want to get the value of the node, to visit the node. So result dot push node dot value. Okay, and that's it. Let's try it. Alright guys, we've done it. We have written functions for Inorder, postorder, and preorder traversal on binary trees using a recursive approach. And we have learned that using helper functions is a common way to encapsulate recursive logic, which helps improve code organization, readability, and modularity, making the code cleaner and more maintainable. A very important algorithm to make sure that you're familiar with before technical interviews is backtracking. In plain English, to backtrack means to go back along a path that you have just followed. When it comes to algorithms, backtracking is a problem-solving approach where we try different options. And if things don't work out, we go back and try something else. It's like exploring different paths until we find the right one. To understand it better, let's take a common yet super fun interview problem as an example. The problem is called Rat in a Maze. And yes, you have guessed it. There is a rat in a maze and the objective is to find the path out of the maze. Let's begin by recreating the maze in a 2D array where 1 represents an open path where the rat can go through and 0 represents a wall or a block. Now let's imagine we're this adorable rat and we want to cross this maze and get to the cheese. How would we do that? First, we're going to go to the first slot at 0, 0. And then we're going to try to move. There are 4 moves that we can attempt, and every time we attempt them in the same order. We can go down, we can go to the right, we can go up, and we can go to the left. So first, we'll try going down here at 0, 0, but it's blocked. We can't go down. So we'll just apply the second move. We'll go to the right. Then we're going to try going down. Oh, we can go down. Great. Next, we're going to try going down again. Oops, we can't go down. We're going to try to go right. We can't go right. We're going to try to go up. Oh, we went up. We'll do the same thing again. We're going to try our 4 moves until one of them allows us to make a move. We'll try going down. Oh, we can go down. Great. And then we'll try to go right. Nope, we can't go right. So we'll go up again. And then we'll apply the moves again. So we'll go down and then we'll try going right, but we can't go right. So we'll go up again. And then you guessed it. We're just going to go down, try to go to the right, go up again, and so on. It's an endless loop. So how can we get out of this loop and make it to the next slot? What if we mark each slot we visit as visited once we visit it? So let's go back to slot 0, 0. And since we're on it, let's mark it as visited. And now to move, we're gonna do what we've done earlier. We're also gonna try moving down first, but we can't because it's blocked. So we're gonna try going to the right. We go to the right, and since we're in this slot, we'll mark it as visited. And then we'll try to go down, and we can go down. So we're here now in slot 1, 1. So we'll also mark it as visited. Now we'll try to go down. We can't. We try to go to the right. We can't. We try to go up, but the slot is marked as visited. So let's try going to the left. We can't. Uh-oh, looks like we're stuck. What should we do? What we can do is change visited from true to false, which will allow us to visit it again. And once we're there, we will return the visited tag. And then we're gonna first try going down, but we've already visited the slot. We'll try going to the right, and we can't go to the right, so we'll just go to the right. We'll mark the slot as visited. Then we'll try going down. We can't, so we'll go to the right, mark the spot as visited, and then we'll go down, mark the spot as visited, go down again, mark the spot as visited, and then go down again, mark the spot as visited, and we did it! We can eat the cheese! Yay! That was pretty simple, right? Let's code it. So we've already created the maze. Now let's define the function that we're going to use to solve the maze. Let's call it solve maze. So function solve maze. And the function will take the maze as a parameter. Now let's declare a variable to hold the number of rows in our maze. and it will be maze.length. And now let's declare a variable to hold the number of columns. It will be maze0.length. We are going to use these values to create an array where we're going to keep track of which slots were visited. New array, and we want an array with the number of rows, and we will fill it with false, and then dot map. We will have as many arrays as we have columns in there, so array calls dot fill false. All right, now let's see if we've done it correctly. So console log visited, and let's run our function solve maze and pass in this maze as an argument. Okay, node rat in maze. Yes, and this is what our visited array looks like. Okay, so in order to keep track of the movement of our rat, let's create an empty array and call it path, and that's where we're gonna track the movement. Now, since our rat will start out at point 0, 0, so let's begin by pushing point 0, 0 to our path array. So path.push 0, 0. All right, let's also mark point 0, 0 as visited. So visited 0, 0 equals true. Now let's create a helper function within our function, and let's call it findPath. The purpose of findPath is to explore the maze and determine whether a valid path exists from the starting point to the destination. It takes in x and y as params. X and y represent the position where the algorithm is currently exploring. All right, now let's add in the base case. The base case checks if the current position is at the bottom right corner of the maze. Because if this is the case, then that would mean that a destination was reached. If it turns out that a destination is reached, the function adds the current position to the path, logs the solution path, and returns true. Okay, now it's time to write the recursive case. Since the entire logic of our recursive case relies on movement, let's begin by creating a moves array, which will define the possible directions that our algorithm can explore from each position. Okay, and now we're going to create a for loop, and we want to iterate through the possible moves. And now we need to check for a valid move. To do that, we have to check is the new x greater than or equal 0, and if it's within the range of rows. Likewise, we have to check the same for y. We check if it's greater than or equal 0, and if it is within the range of columns. And we should check if the slot that we're moving to is open and it's not blocked. And as you remember, when we created the maze, we decided that 1 means open and 0 means blocked. We also want to check if the slot has not been visited. Okay, so if these conditions are met and we have a valid move, then we want to take that valid move. We will push the new x coordinate and the new y coordinate to our path. And we also want to mark the slot that we've added to the path as visited. And why not console log where we are. Okay, now let's add a recursive call to keep exploring, and here it is. Actually, this is not just a recursive call. We've also added an if statement. We're checking if our find path new x and new y function returns true, because if it does, then we know that we have reached the destination and we don't want to keep going. Anyways, if the condition returns false after our function reruns, then that means that we need to backtrack. We backtrack by removing the last position from the path and changing its visited status from true to false. Finally, if there are no valid moves from this position, then we want to return false. And now it's time to create a function call to initiate the maze exploration from the top left corner, and it would look like this: find path 0, 0. And in case there is no valid path found, we want to inform the user. So if not find path, we want to console log no valid path found. All right, let's run our function and see what happens. So node rat in maze. All right, so we got the solution path. However, I would like to see when it backtracks. So I'll go to where we've added the backtracking logic, and I'm just going to add this line, console.log backtracked from, and that way it will tell us when it backtracks, and it will tell us the coordinates it backtracked from. Let's try it. So node rat in maze. Okay, awesome. It backtracked from 0.11 exactly like we did when we tried running the maze before writing the code, remember? We did it. Yay. We have just helped the rat escape a maze through the use of backtracking and recursion. Isn't that awesome? This brings us to the end of our recursion exploration journey. If you found this video helpful, please like, share, and subscribe. If you have any questions, please leave them down below. Thank you so much. Have a lovely day and see you next time. Goodbye.